All right. Hi, everyone. My name is Brooks. I am an ecosystem engineer here at GitHub, where I work on our APIs and webhooks. And today, I'd like to talk about launching GitHub's GraphQL API. But before I dive into the GraphQL API, how it works, and ultimately our decision to use it, I'd like to start with the story of the GitHub API. Now, GitHub.com is almost a decade old now. Shortly after the launch of the website, the first API endpoint was added to the application, and it unsurprisingly allowed you to fetch data about commits in a variety of different response formats. One of those response formats was JSON, the same one that we use today, XML, which was very popular at the time, and even a response format called YAML, which was a fun fact that I learned in researching this talk. Now, after about a year, API v2 was released. And this gave GitHub the chance to evolve the API based on the lessons learned in the first iteration. Now, this is sort of the natural progression of REST APIs in general. API designers version them as they learn more about the way that people use them and as they gain a better understanding of how to best model their data. In April of 2011, API v3 was released, and this was a pretty significant change. We had dropped support for XML and YAML and standardized on this JSON response format. Now, for all intents and purposes, this is the same API that we use today, almost 6 years later. The only difference is that over the course of those last 6 years, we've added more to the REST API as new features are released. Now, I'd like to take a quick detour to discuss the way that REST APIs work to better understand our thought process when we were designing the next version. When interacting with a REST API, there are a few different components to your request. The first is an HTTP verb, and it specifies the operation that we'd like to take against the API. The second is an endpoint, and it's an identifier that allows us to specify which part of the API that we'd like to interact with. When we make a request to this endpoint, we get back a response that looks like this. In this case, it's JSON. And JSON is comprised of keys in green on the left-hand side and values in red on the right. Now, REST APIs, they return resources. And resources are a way of describing a particular object, things like a pull request, an issue, a user. And if we take a closer look at what one of those resources might look like, and we zoom in on that, we can see that a resource is comprised of a series of attributes that are tied directly to the object. In this case, we're using the /user endpoint to fetch a user resource. And there are attributes like name, location, and email, all of which that describe that user. But we don't always think of these resources in isolation. Commonly, you see attributes that refer to associated resources to make it easier for users of the API to get all the information that they need in a single request. In this example, you can see that we've added counts of repositories and gists as they relate to the currently authenticated user. But what if we wanted to fetch more information about these associated resources? API consumers typically need to fetch multiple different resources in order to build the full picture of data that you may need for your applications and integrations. So in order to help fetch those associated resources, Hypermedia was introduced to the API, the v3 API, in August of 2011. Hypermedia is a machine-readable link to another place in the API about information related to the resource at hand. Here you can see a URL that will tell you more about the repositories for the currently authenticated user. In this case, it's myself. And if we make a request to that endpoint, we get back a response that's now describing a different set of resources. In this case, it's that list of repositories. And again, you can see that there are attributes describing this new resource and even more hypermedia pointing to another resource. And if we make another request to that endpoint, we get another response of keys and values that are now describing the issues of each of the repositories that belong to that currently authenticated user. We can use Hypermedia as a way to navigate the data graph of an API. If you imagine that we have a desktop application, you can see that it takes numerous different requests to get all of the information that we may need. One request to for the currently authenticated user, another request to fetch all the repositories, and then for each of those repositories, fetch a list of all those issues. This can be especially painful when working with a mobile client that might have a really slow connection, say like a 2G connection. So REST APIs are modeled around the resources that they return. And this makes them general purpose and reusable from client to client. And that's one of REST's biggest strengths. But one of my favorite questions as an API engineer is how can we create a better developer experience for the users who consume these APIs? And that was the major question that we were looking to answer when we started to explore what the next version of the API might look like at GitHub. And that's where GraphQL comes in. So to tell you a little bit more about GraphQL, it's a data query language for your APIs. So think of it as SQL, which is the lowest common denominator between technologies like MySQL, Microsoft SQL, Postgres, and so on. And think of it less as Neo4j, if that's something you've heard of, which is an entire graph database in its own right. So GraphQL is a query language specification, and it's been implemented in a variety of different languages like Ruby, JavaScript, Scala, Python. And the language was originally created by Facebook to help with the data access needs of their mobile clients. Dan Schafer, one of the co-creators of GraphQL, came to Universe last year to talk about their story. This is the hello world of GraphQL. Right off the bat, you'll notice that it bears some resemblance to JSON. It almost looks like JSON, but without any of the corresponding values. And that's very much on purpose, and we'll see why in a few. So there are a few different components to a GraphQL query. The first shown here is viewer, which represents an object that has more information that it can return. The object in this case is the currently authenticated user, which is similar to that /user endpoint that we saw earlier. So for the currently authenticated user, we'd like to fetch their name and email. We call these fields, and they're a selection set of the object. When we execute a query against the GraphQL server, we get a response that looks like this. Now, you'll notice that the query has defined the shape of the response, and that's an important part to GraphQL. If we wanted to send a request to a GraphQL server, it might look something like this. We still have our HTTP verb, and we still have a point, but it's pretty much for the similarities with REST end. Now, the reason that we use a post is because the client must send some data to the server, and that data is the query that we would like the server to execute. That query might look something like this. In this example, we're trying to fetch information about a specific user. In this case, it's Defunct, our CEO, who we just heard from in the keynote. And in order to specify the user that we're referring to, we use what's called an argument. An argument is a way for us to pass relevant information to the server so that it can modify the response based on the information that we're looking for. And if we send that query to the server, we get back a response that looks like this, again, where the query has defined the shape of the response. So there are a few features of the query language that I'd like to really dig into. The first is that GraphQL is typed. And the type system is a product of the application code that GraphQL sits on top of. When we look at that hello world example, behind the scenes, there's actually something that we call a schema. And it's this schema that GraphQL is capable of querying. It might look something like this for this particular query. Now, I should point out that this schema is pretty much imaginary, and behind the scenes, it's something that we, as users of the API, really don't have to worry about much. But it is useful for understanding how GraphQL works under the hood. We call this notation on the right-hand side IDL, and it's a way of describing the schema. If we break down the query on the left line by line, you can see that each part has a corresponding entry in the schema. The viewer field lives at the query's root. I'm seeing that on the top right-hand side of the screen. And it returns a user object type. Remember, objects in GraphQL have more information that you can ask of them. The user type implements two fields, name and email, both of which return what we call a scalar value, just a string. If we look at our example where we're querying for a specific user and its corresponding IDL, again, we can break down each part of the query and see how it relates to the schema. We start with the user field in the query's root, and that user field takes an argument named login, which must be a string, and that's something that the schema mandates. What's cool about GraphQL is that it's capable of validating queries before it does any sort of heavy lifting, and that's the power of the GraphQL type system. If the user passes in anything other than a string or for login, it can return a helpful error message and say that it was expecting something else. So similarly to the last example, the user field returns a user object type, and that object type implements both name and bio, which are a string. So what if we wanted to fetch a list of objects? This query will return a list of all the open source licenses on GitHub, their name, their nickname, and their URL. Here we can see that the licenses field returns a collection of license objects. You'll notice that it's followed up by an exclamation point in the schema, and that denotes that the field is non-nullable, meaning that you'll always get back at least an empty array. Here we can see that the licenses field returns that collection of license objects, and a license object is composed of a name, a nickname, and a URL, where name and URL are guaranteed to always be present, but we may not always have a nickname. Another feature of GraphQL are aliases. Let's say that we wanted to fetch two users by their login, Chris and myself. If we were to execute this query, we would expect to get a response that looks like this. Because the shape of the query defines the shape of the response, we'd end up having a key conflict, which isn't quite legal JSON. Aliases can be used to assign a different name to a part of a GraphQL query. And if we execute this query, we'd end up with something like this, where instead of having user for the keys, we have our aliases, Chris and Brooks. Next up are fragments. You can imagine that over time, queries might grow to be large, unwieldy, and repetitive. Fragments are a powerful tool to reuse different pieces of schema. If we take a deeper look from our previous example, we can see that there's some duplication there. Name and bio are reused in both of these user lookups. We can use a fragment to deduplicate what we want for each user. Fragments use this ... notation followed by their name, and that's how you reference one. The fragment itself is defined at the bottom of the query, where we've named it user info. We've specified that it will always be called on a user, and for that user, we would always like its name and its bio. Now, in some cases, you may dynamically change pieces of the query. Variables give you the option to do so. You'll notice that in all of my previous examples, I've started every query off with an open curly brace. But actually, there's an implicit keyword there called query. And it specifies that we're trying to gather information from the API. Both this query keyword and that open curly brace are totally valid GraphQL syntax. Now, like fields, the query keyword can take arguments. The arguments that it accepts are the variable names and their respective types that we intend to use throughout the rest of the query. We just have to remember to send along the contents of those variables to the server when we execute our request. It might look something like that. Now, when we make that request, we get back a response that looks just like what we would normally expect, where the query has defined that shape of the response. Now, as I alluded to before, GraphQL servers aren't just capable of querying data. You can also modify data with what we call mutations. In this example, I'm looking to create a new project board for one of my repositories. We can use the mutation named createProject to do so. CreateProject is an action that's been defined on the GraphQL server. In this case, I want to create a project in the repository, which has an ID of 1234, and I'd like to name that board to-do. What's interesting about mutations, though, is that they're capable of also querying data once the mutation is complete. In this example, I'm asking for the project's URL right after it's been created. And we get back a response that, again, looks like that. All right, and the last major component that I'd like to cover is Relay. Relay is an extension to the GraphQL specification that gives us more flexibility when paginating over collections of objects. It adds the graph to GraphQL because really we think about our data and graphs, not necessarily resources with well-defined boundaries. So Relay gives us a few things. First, it can tell us metadata about the collections of objects that we're referring to. In this example, we can determine the total number of repositories that the currently authenticated user has access to. That would give us a response that looks like this. Next, we can pass arguments to these collections to tell the server how many items that we'd like back at once. In this case, I'm just asking for the first two repositories that belong to the currently authenticated user. Next, we query the edges of the graph. Edges are a concept that help us conceptualize and store data related to the one-to-many relationship between a viewer and all of their repositories. We can think of edges as the blue lines that go from the user to each of its repositories. Nodes, on the other hand, are the respective repositories that are on the edge of each of those edges that belong to the viewer. So off of each of those edges lives that single node, a repository. And for each of those repositories belonging to the currently authenticated user, I'd like to fetch their name. If we execute that query, we get back a response that looks like this, where I have a collection of edges for each of the repositories that belongs to me. But how would we go about getting the next two repositories that belong to me? The last major component of Relay is cursors. Cursors refer to the position in a collection in which an edge may reside. So if we take the last cursor from our response, we can pass that into that same query to get the next two repositories after NYC Restaurant Grades and LaunchBar GitHub. Something like this, which would give us this response, which is the next two repositories that I own. So another feature of GraphQL is that it's introspectable, meaning that it's capable of telling you all the things that it knows how to query. With the power of a type system and introspection, this means that we get documentation and client generation for free. Now, one tool that utilizes the power of introspection in this type system is something called Graphical. Graphical allows us to craft a query on the left-hand side of the screen and get immediate feedback on the right. You'll notice that as I start typing into Graphical, it gives me some hints based on what I'm typing. And this is because Graphical knows where I am in the schema at any given time and can offer suggestions of what's available to me. In this example, I'm just asking for the currently authenticated user's login. In addition to giving this context-aware type ahead, Graphical has a built-in documentation explorer that can be a really handy reference to determine what else is available to me for another object. Now, if I browse through that documentation, I can go back to the query root to determine what top-level queries are available to me. Here I can see that there's a top-level licenses collection, and the license object implements a variety of different fields there. Let's say that I wanted to fetch the name and the description of every open source license that's on GitHub. Now, once executed, I'll get back an array of these licenses with the fields that I had requested, the name and the description. But let's try something that uses Relay. Let's say that I wanted to query a particular user. As I start to type out what the top-level user field, Graphical knows that it requires login. I choose defunct, and for that user, I'd like to fetch the total number of repositories that that user has. Now, in addition to fetching the total number of repositories, I'd like to also determine the size those repositories use. I can use the total disk usage field to do so. So let's take it one step further. Let's fetch the name and the name of each of those repositories. In order to do so, we'll need to fetch the repository edges, and off of each of those edges, the node, and from there we can fetch that repository's name, just like that. So these are all the repositories that defunct has access to. But as I mentioned earlier, we can use aliases as a way to change the way that we name something in the response. I find edges and nodes a little bit easier to comprehend if I rename the node the singular version of the collection that I'm referring to. So in this case, it would just be called the repository. Now in the response, I can see that I'm iterating over a series of repositories, and then I have a single repository each time instead of the word node. Now, one of the biggest strengths to GraphQL is its ability to fetch a variety of different types without having to make a number of different requests. Let's say that we want to fetch each of the issues off of each of the repositories that belong to that defunct user. Here I'm fetching the last 10 issues of those repositories, and for each of those issues, I'd like the title and the login of the author that created them. And finally, let's get each of the comments for each of those issues. I can use that same sort of edges and node syntax that comes from Relay to fetch the last 10 comments and their body. Of course, I can also use aliases to rename that node to comment as well. I'm a really slow typer. So you may have noticed with GraphQL, or Graphical rather, we were able to nest multiple different resources into a single query. So if you think back to our earlier desktop application where we had to make numerous requests to get all the information that we needed, now that application can make a single request to the GraphQL endpoint. So going back to the question that we were asking ourselves when we started work on the next version of our API, we realized that GraphQL was standing out as a great contender to offer a better developer experience to our users. So in early 2016, we started work on what would ultimately become the next version of our API. That journey started on March 20th, 2016, when the original proposal for GraphQL at GitHub was submitted. A few weeks later, a proof of concept was done, and it allowed us to do simple things like query for repositories and users. But after seeing it, we all started asking each other, if this is what we can do in a matter of a few weeks, what could we do with it over the course of a year? Shortly after the proof of concept was complete, a new team was created to focus on taking that proof of concept and see how far that we could really take GraphQL in our code base. After 8 months of hard work, we released the GraphQL API in early access at GitHub Universe last year, and this was an opportunity for us to get feedback from our users on this new API. At GitHub Satellite this year, we launched the production version of our GraphQL API, API v4. And if you fast forward to today, we're executing over 200 million GraphQL queries every day. One of the first hurdles that we had to overcome was how to effectively rate limit in GraphQL. In the REST API, as an authenticated user, you're granted 5,000 requests an hour. Now, there are a few abuse limits in place as well to help protect the system and ensure that you're using the right tools for the job. Now, the reason that we have rate limits in place is not to deter users from fetching too much data. It's to make sure that they're doing so in a performant and efficient way that experience of other users. So when we started to explore what rate limiting could look like in GraphQL, we had hit a snag. A single request to the GraphQL endpoint has the potential to return far more data and be much more taxing on our systems. So we ended up with a two-part solution. The first is that you can only receive a maximum of 500,000 nodes at a time for a single query. After that, you need to paginate over your collections using those cursors that we saw in Relay. And the second is a scoring system that's based loosely on the number of collections that you're fetching and how they relate to our underlying data access infrastructure. When executing a query, you can ask for the rate limit statistics when they're currently available on the bottom there. And if you pass the argument dry run with a value of true, you get back only what that query has the potential to return in terms of node count. This is one of the only parts of our GraphQL schema where the shape of the query doesn't necessarily showcase the shape of the response. And you can do the same sort of dry run execution to determine what the query would cost against your allowance without actually affecting it. So a large number of those queries that we execute are actually coming from inside the GitHub application. And that's because over the course of the past year, we've changed the way that we build new features at GitHub. We're taking an API-first approach. Previously, the way that a feature would be built is that an engineering team would start creating the user interface for that new feature. Once the UI is complete, the engineering team releases it to others at GitHub in a process that we call staff shipping. Once that feature goes through a final set of iterations based on that feedback, it goes to production. But it won't until the weeks after it's been launched that work on the corresponding REST API would begin. But today, all new features are built with GraphQL from the start. By doing this, we end up building a platform that's shared between our engineers internally and our users who otherwise wouldn't have direct access to our data. So this is to build a true public API, something that's in sync with new features as they're released. But in addition to just the next version of our API, this allows us to build a platform where everything is shared between our internal engineers and you, our users. I had mentioned earlier that a large majority of the requests come from internal queries. When we do feature development for the UI, we're using a library called GraphQL Client. And this is something that we've built in-house to help facilitate the execution of those internal queries. It allows us to exchange a query for Ruby objects so that we can co-locate them inside of our views. And this is a pattern that you may be familiar with if you've heard of React. It looks something like this, where we can execute our query in our controller, and then in our views, we can inject that response. We can access them as a series of Ruby objects. This just goes to show that we are our own consumers of the GraphQL API. The only difference is that instead of us using that /GraphQL endpoint, we're using this gem to help get the responses back in Ruby. This is just one of the ways of modifying the GitHub application to be API first. Now, another part of those 200 million queries a day that we execute, interestingly enough, comes from the REST API. Because all new features start with GraphQL, that means that in order for us to create a REST API for these new features, under the hood, we actually need to execute a GraphQL query. We then take that response from GraphQL into a format that looks and feels like a REST resource. REST APIs, we use another library called Scientist. Scientist gives us a chance to verify that the data we're returning from GraphQL is correct and valid. So the way that Scientist works is that it executes two code paths at once, a control and a candidate. but only the control is ever actually returned to the end user. In this example, let's say that we were trying to back the /user endpoint with a GraphQL query. The control in this case would be on the top. It's the legacy code that we know has always worked. The candidate would be this new GraphQL query whose response we take and we make it look and feel like a REST resource. Once Scientist has executed both of these code paths, it allows us to compare both of them for accuracy. Now, in some cases, there might be mismatches between the control and candidate, and that's an opportunity for us to figure out what might be causing it. Scientists can also compare the speed at which the control and the candidate execute, and that's been a powerful tool for us to figure out what needs to be optimized first. And there have been a few tools that we've helped build to onboard users into this world of GraphQL. One of my colleagues, Garin Tarikian, built a tool called GraphQL Docs, which powers one of the pages on the developer.github.com website. This tool utilizes the power of GraphQL's introspection to display documentation in a clean and elegant way for users to view. Now, the cool part is that this all happens automatically. We don't have to write any extra documentation outside of what's inside of our schema when we craft it. Last week, we shipped an automated changelog, which automatically updates a page on developer.github.com with all of the additions and modifications we've been making to the GraphQL schema. Last year at GitHub Universe, we launched a community website that we use as a platform for discussing bugs, feature requests, and new ideas for the GraphQL API. You can see that at platform.github.community. So what's next for the GraphQL API? One of the biggest things on our roadmap is gaining confidence in the coverage of the GraphQL schema. And that means that making sure that you have everything that you need in order to make applications and integrations using GraphQL. We know that the GraphQL API isn't fully there yet, and it's going to take us a little bit of time to get there. But the big question on everyone's mind is what's happening with the REST API? And the answer is that we intend to fully support the REST API until we have the confidence that the GraphQL schema has as much coverage as needed to empower your workflows. One of the next major components of our roadmap is a GitHub Apps integration. One of the best parts of GraphQL is that it gives you finer-grained access to the data that you need, but that doesn't jive super well with the resource-based OAuth scopes that we currently require. GitHub Apps will give us the opportunity to better align fine-grained authorization with fine-grained data access. If you'd like more information on GraphQL, you can check out our documentation on developer.github.com, or you can check out the entire specification at graphql.org. I also encourage you to check out the platform.github.community website if you have any ideas or feature requests that you'd like to share for the GraphQL API. And finally, I'd like to thank all the people that helped get GraphQL to where it is at GitHub today. There are countless engineers, members of our support team, our quality team, and our documentation teams who've helped shape this project and worked with us as we went through this new process. I'll be around later today at the Ask GitHub booth in the back there if you have any later questions. Thank you.